Señores, buenas tardes. Ladies and gentlemen, good evening. I'm very pleased to be with you for this presentation. I am also very pleased to be in the Basque Country I love. And so I will, okay, so I see, okay, so it begins to be on the screen. So my talk, you see, first, on the first projection, on the left, on the right, you can see an artist's view of what can be called the digital age. That is, with this explosion of many transfer, creation, transfer, and processing of digital information of today. So my talk will be rather or more on the high side, that is, on the, to show that the roots of all this technology have been in creation by fundamental research, by research on mainly on the physics, on quantum physics, on condensed matter, the condensed physics of material, condensed physics of magnetic metals, for example. And the research is going on in this direction, and there will be other discovery to advance this field. But the second point is also very important. Today, a challenge today is also to reduce the huge consumption of energy by all this technology. To give a number, 7% of the electricity consumption in France, and even more in the US. And so for us, it is a very motivating challenge to reduce, to find a new, to discover new effects that are able to produce new components to reduce the energy of all this information technology. And, okay, and what is following? So, okay. And so we'll see that, in fact, and for example, there is, again, we are working to improve the components of the digital technology. For example, one of the results of the field of research, which is called spintronics, is today the beginning of the massive production of new components for computer called STT-RAM, STT random access memory, that are components that consume less energy than the RAM of today. And that certainly will be integrated progressively in the next generation of low-power computer and telephone to reduce definitely the energy consumption by computer and telephones. And for telephone is also interesting. And we are also working on another direction, not direction what is called neuromorphic computing. That is computer inspired by the operation in the brain. And also this, we are presently working in my lab, working on specific components to reproduce the functions of the synapse and neuron. And this also is a promising direction for computer with interesting possibility and also a small consumption of energy. Okay, digital and digital age. So in the preceding talk was on quantum computing. Alors, you have seen that quantum computing will be a huge interest for very big calculation, very fast calculation that can be performed by the digital computer of today. Of course, when this computer will arrive, they will go into our computer. They will be integrated into big systems generally at low temperature, certainly, that is at the temperature of few degree Kelvin, and so it's something completely different. They will be extremely useful for some time of calculation, but it's not exactly the same road as the information technology I am talking about. And also, okay. So to give some number on the explosion of the information technology, I give some number. you can see, for example, this never of data on 2012, but they are more or less the same. So one say in 2 days today, every 2 days we create as much information as we did from the beginning of the time up to 2003. And so the increase during something like 10 years is a factor of 50. So there is a huge quantity of information which is treated by all this technology. And of course, so the fantastic advances in the technology, but many societal questions. Yesterday, Arosh has spoke about some problems like the propagation of fake news, which is favored by this technology, and the addiction of children to virtual reality. But I will not speak of this societal problem, but only on the problem of the energy consumption and the challenge and the danger for concerning the emission of carbon dioxide and climate warming. So to give some number of the consumption of energy by the computer, you consider one of the data center of Google in the United States, the consumption of energy is the same as the town of San Francisco. So something very big, and so there are many data centers in the world, and finally this is data center energy which is increasing more and more today. To have a more personal feeling of the consumption of energy by us, 30 Google search costs as much energy as to bring a liter of water to boil. Okay, so you see, even when you are simply clicking on Google, you spend a lot of energy. It is much better for you to store the links you want to go, the usual link, rather than every time searching via Google the links. Okay, so I'll show you now an overview of my talk. The first part will be, I will give an example of technological advance due to fundamental physics. How the discovery of what is called the giant magnetoresistance, GMR, of magnetic multilayer has led to many applications, and specifically to the application to the storage of information in the hard disk for an increase of the capacity of the disk by about 1,000. The second part of the talk will be on in fact, the discovery of the GMR also has kicked off the development of a new field of physics which is called spintronics, a sort of electronics harnessing not only the charge of the electron as classical electronics, but also the magnetic moment, the spin that has been introduced in the precedent of the spin of the electrons. And for example, we showed that one of the results in spintronics leads today to the massive production of STT-RAM, STT-RAM that will be introduced, component for computer that will be introduced progressively in the next generation of computer to decrease the power consumed in computer and telephones. The third part of the talk will be on the perspective for brain-inspired computer able to learn like our brain. And finally, the last part will be on the perspective with novel magnetic quasi-particle called skyrmions. I will explain what are these skyrmions, and the perspective for the treatment and storage of information. So I begin with the first example of, and so the discovery of the GMR and the application to the storage of information in the hard disk. And so, in fact, we can see on the left a hard disk of maybe 30 years ago, and the new hard disk, this is the hard disk of the data center, the type of hard disk in your computer, and you can see the capacity has been increased by more than 10,000 between two, 100, even more, 10,000. Okay, and and will explain how it could be obtained. So this is a schematic of a hard disk, so it's a disk covered by a magnetic film with the head of the disk that can be moved mechanically on the disk. And the information is on this circle, these tracks, and the information is stored by magnetic domains, by magnetic pieces of the film with the magnetization up or down. And of course, what is difficult is we want to have many of these bits on the disk, to have very small bits, but when the bits are very small, they become very difficult to detect. And so the limitation for the capacity of the disk was reading very small bits. And now it is done by using the GMR, giant magnetic resistance of magnetic multilayer. Magnetic multilayer is, for example, a very thin layer of copper, 3 atoms from one side to the other, 1 nanometer between 2 magnetic layers. And the property of the GMR that I will explain is that when the magnetization of the different layers are random, the current cannot flow in this film, but when a small film, even a very small film, aligns the magnetization of the layer in the same way as a field aligns all the needle of compass in the same direction, then this film becomes conductor and it is possible to detect with a great sensitivity the information on the disk. And so I will explain how this discovery came from advances a long time ago in fundamental physics. Okay, so it was to explain what is a magnetic material. A magnetic material is a material in which with different number of electrons having their spin in the direction of the north and south pole. We can say spin up and spin down electrons. And the general property is that the electrical conduction is more or less independent by 2 channels, one for the spin up electron and the other for the spin down electrons. And one of the results, it was a result in my PhD, it was that in some materials, in some alloys, it was possible to obtain a strong contrast, very strong conductivity between the 2 channels. For example, nickel with chromium impurity was more or less stopping the electron in one of the channels, and the electron can flow only in the other channel. And so this was a result from the theory of solids developed, for example, by Friedel in France. And in this case, why chromium impurity has this effect? Because there is something which is called the resonance scattering of conduction of the wave function of the conduction electron on the levels of the chromium impurity. So it's a question of quantum physics that can be described by Schrödinger equation and so on. So what occurs in this case, if one put a magnetic layer on the way of electron, this magnetic layer will stop the electron having their spin down, and only the electron with spin up can go through. But this is we expect, on the contrary, if one reverses the magnetization of this layer, then it will be the opposite effect, that now the spin down electron can go through and the other are stopped. It's not exactly as they can go, but weakly they can weakly transmit. And what is the concept of the GMR is making a multi-layer like this one. And if the magnetization of the 2 layers are opposite, that means that these spins, this electron will be stopped by this layer and the other by the first layer, which are opposite. And so the current cannot go through this bilayer. And on the contrary, if a magnetic field can be very small, align the magnetization, that means that this spin direction will be we can go through, only this one will be stopped by all the layer, and so there will be the current. This opens the way to the electrical currents. And this concept can work not only when the current is perpendicular to the layer, but also if the current is along the layer, like this one, because the trajectory of the electron is not strictly a straight line, but there is some zigzags like that, the effect is similar. In fact, the concept, we had also this concept at this time, at the time of my PhD, but in fact, we know also physics at this time. And we knew also that this concept can work if the distance between the two layers is shorter than what is called the electron mean free path, something which is the order of one of a few nanometers. That is the size, the space for only a few atoms. And at this time, the technologies did not exist to prepare very thin layer like that. And so we have to put the idea in the fridge and to wait some time. And then the technology, like some technology appear in the development of microelectronics technology, for example, that this one, very complex technology that today and from the middle of the 80s enable people to deposit very, very thin layers, say 2 atomic layers or 3 atomic layers. And then we adopted, in a collaboration with a company on microelectronics, this technology to prepare multi-layer like this one, three atoms of iron, 3 atoms of chromium, and so on. And this was the discovery of the GMR in Orsay, and at the same time by Peter Grunberg in Jülich in Germany. And so this is our result in Orsay. It was in this type of multi-layer iron and chromium. And you can see if the chromium layer is really thick, thin, very thin, less than 1 nanometer, by applying a field to align the magnetization along the same direction, the resistance drops by 80%. So we call it giant magnetoresistance. And this giant magnetoresistance has been rapidly applied. The first application were to prepare a magnetic sensor for the sensors that we have in your car. In many cars today, you have sensors to detect the rotation of the wheel and so on, based on the GMR, and rapidly, only 6 years after, to the hard disk. And so multi-layer is introduced to detect the very small fields created by small bit, and this enable the technician to decrease the size of the bits, and so to increase the density of information in the disk by a factor of 1,000. And to also extend this technology with very small disks to mobile electronics, cameras, iPods, and so on. So to summarize, okay, something interesting to note is, in fact, as many times in science, the discovery came for the meeting between 2 directions of science. That is, the development of new ID on the conduction in metals, and other side, the development of technology. And the encounter between these 2 directions led to the discovery and then to the application. And of course, once a discovery has been obtained, okay, the discovery also is at the origin of many other developments. And in the case of GMR kicked off the development of the field of science called spintronics. So, as I say already, a type of electronics harnessing not only the charge of the electron, but also the spin of the electrons. And this spintronics today is developed in many directions. And so I will take example of developments in first, in classical electronics, as I take the example of applications, the STT-RAM for the next generation of low-power computers and phones. And so I will say rapidly a few words also on computer inspired by the brain, and also a few words on these new animals in the nano world called skyrmions. So, development of spintronic and the emergence of spintronic components for low-power computers. Okay, in your computer, of course, you have a massive memory in the hard disk, or in some computer, if you don't want to have a massive memory, you can have some memory in flash memory. But then the access time to the disk is very long, milliseconds, and compared to the speed of computer today. And so first, when we switch on your computer, you store a part of the memory in the RAMs, DRAM of SRAMs, that memories with very fast access. You can access very rapidly to the information in the range of the nanosecond. But these RAMs today are volatile. That is, simply to keep the memory alive, you have to put electrical power in the memory to keep the memory alive. And so this is one of the main sources of energy consumption of the computer today. And so for a long time, it has been objective has been how to fabricate non-volatile memory that can keep the memory without furnishing energy. And so the new in spintronics, the new type of non-volatile memory is the MRAM and the STT-RAM. MRAM, okay, the MRAM exists has been introduced into the market a long time ago, and so it exploits a quantum effect, which is quantum tunneling of electrons through a insulating barrier. For example, you have this sort of structure seen by electron microscopy with a very thin 1 nanometer of alumina insulating between two metals. And so, in principle, at microscopic scale, the current cannot go through an insulator. But if the thickness is very small, there is an effect which is called quantum tunneling of the electrons that is due to the fact that the wave function of an electron is not localized at a given position, but extend a little more. And so if the distance is small, or the range of the nanometer, it extends on the other side of the what is called the tunnel barrier, and it gives a probability of tunneling. And so, and the TMR, the tunneling magnetic, is the fact that when the electrodes are magnetic, the current, the resistance of the tunnel junctions is very different for the parallel and opposite magnetization of the two electrodes. And this is the base of what is called the MRAM, cut into this multi-layer with this tunnel junction, some pieces like that. And this is a memory with 0 and 1 for the parallel and opposite configuration of the magnetization. And this type of MRAM exists since 2006, but it was not good enough to be introduced in the computer, but it has been introduced in avionics, in space, because it has another property. It's not sensitive to the radiation of the atmosphere. So it has been a niche market, has been for avionics, for example, Airbus, important for Airbus. But now, in the recent year, there was some fundamental advance, first in the understanding of the tunneling effect, the preparation. You can see a tunnel junction, an image of the tunnel junctions. The dots are atoms. So a tunnel junction with a insulating barrier of magnesium oxide between, and this junction first gives very large TMR, and finally the STT-RAM as the schematic is this one. So there is a reference layer with the magnetization in the direction, the free layer, magnetic layer, with two opposite possibility direction of the magnetization correspond to 0 and 1. So the state, memory state correspond to this orientation. The reading is, of course, by detecting the difference in the tunneling of electron between the two configurations, 0 and 1. And the writing is obtained by a new interesting effect, which is the spin transfer torque that is simulated here. One sends in a magnetic material a spin polarized current, a current with a current spin, and there is a transfer of the quantity of spin to the total spin, and it can be electrically it is possible to switch electrically any magnetic material, and this is a very local manipulation of magnetization that is used in this spin transfer torque RAM, and this is an image of a spin transfer torque RAM. The diameter is only 20 nanometers, and this is the basis of the STT RAMs that begins to be produced massively by some big company, with the advantage of non-volatility and low energy consumption. And so there is, 2 years ago, there were many announcements of the beginning of massive production of this STT RAM, for example, by Samsung. Samsung has already the STT RAM in one of the last phones, and several companies are developing. Of course, the introduction in our computer will be progressive. It's not possible to introduce brutally new components in all the computer, but it begins to be introduced in some computer only in the logic circuits to replace the SRAMs, and progressively the DRAM will be a little longer to replace the DRAMs, etc. Okay, so in fact, to show that in fact we are at the time of some emerging technology for to reduce the consumption of energy by the computer. In fact, this is a prediction of the consumption before this introduction. So you can see that what was expected, the multiplication of the power between 2019 and 2030, there was a multiplication by a factor of 4. And for example, the data center, the factor was even higher. What is expected is a large increase of the energy consumed by the data center. Okay, so brain-inspired computer, characterized by the potential to learning. And okay, so you have already in this sort of picture of the neuromorphic computer AlphaGo, won the champion of Go. And okay, if you want to look at this picture, AlphaGo is a neuromorphic computer with artificial neuron and synapse to simulate the operation in the brain. And in fact, these neuron and synapse are emulated. Okay, nothing else here. Okay. I have always two laser pointers. And I have two ends, one for the laser and one for the, okay. And this one, okay, this one has a switch, yeah. Okay, and so you said each microcircuits, no, it's okay. Okay, I have two. Yeah, for this one too. It's not yours, it's mine. Huh? It works. Oh, I will see. No. But, okay, with this one. Okay, thank you. Thank you. Okay, so in this old-style neuromorphic computer, there are about transistors to emulate a synapse, much more to emulate a neuron, and finally the size of the microcircuits of a synapse of a neuron can go up to 100 nanometers. So you explain the big size of the computer for only a function playing Go. And so this is one of the, it works, but we see it's not is not promising for practical application. If you want to have this big, in fact, if you want to reproduce some other function, you need a computer of the size of San Sebastian. And also you see also the consumption of energy. A few pieces of sugar are necessary for the Go player, and this one, the AlphaGo, is spending much more energy at the same time. And okay, and so what to do to obtain brain-inspired computer less expensive in energy? Okay, what is the origin of the energy expense in computer in general? Is because in computer in general, even in the microprocessor, the information goes as go and back, goes and come back from logic gates to memory, from logic gate to memory and back to logic. And so this is the main origin of the expense of energy with respect to the brain. For the brain, okay, these two operations, memorization and logic, are performed at the same time. In fact, there is synapse between neurons transmitting the information from this neuron to this one. And in fact, the synapse transmits the information, but at the same time, its transmittivity changes, and this is the memory of the synapse. The synapse not only transmits, but takes memory of the information. And so finally, any signal traveling in the brain leads to a restructuration of all the circuits. And so the transmission of information is mixed with the memorization of the information. And at the same time, in the AlphaGo, it was more or less the same because, in fact, the neuron synapse was emulated by microcircuits also with transistor and with the same defect and energy consumption. And so one of the interesting objectives that we can have in this field is to conceive specific nanocomponents acting as nanoneuron or nanosynapse is one of the topics we develop in our lab. And so, for example, we have, I give the reference of this paper, neuromorphic computing with nanoscale. The neuron in this paper is played by a spintronic oscillator. It's relatively complex to explain. I will say a little more on the emulation of synapse by ferroelectric domains. In fact, a synapse, a nanosynapse, only a few nanometers can be, we have developed this sort of nanosynapse, in fact, a tunnel junction, but the barrier here, insulating barrier, is ferroelectric. That is, the current, the transmittivity by this synapse depends on the orientation of the ferroelectric polarization of this compound here. And so there is a factor of, say, 10,000 between the two orientations in some systems of the ferroelectric polarization. And, but in fact, when one sends pulse, the spike of the neuron into this synapse, then the transformation is progressive. Progressive, you see, from blue it becomes progressive to red. So there is each pulse, each spike decrease progressively the transmittivity of the synapse. And this is exactly the function of the synapse. Its transmittivity evolves as a function of the cumulative effect of all the spike it transmits. And it's a little more complex because what has to be achieved also is what is called a spike timing dependence plasticity, that the neuron recognizes if there is a causality between the spike in the preneuron and the spike in the postneuron, if there is a correlation in time between the two. And this can be done also in this system not with a simple spike, but with electrical spike, electrical voltage, which has a very specific form, but reproduce also increasing the transmittivity if there is a positive difference on time between pre and post, or the contrary if we are in the opposite direction. So it works, and finally, I suppose I am not in time, so I will not describe this one. This is a reproduction of the recognition of, by this sort of system with the same type of the recognition of some image, and so the success of the recognition after some learning. But I have not the time to explain, it will be too long, and so I suppose, because I have. And I'll say a few words on the novel magnetic quasi-particle, the skyrmions. What is a skyrmion? Suppose a magnetic layer, a thin film, with magnetization, the spins in the up direction. What is a skyrmion? Is this local configuration of the spin on some neighbor atoms, say 20 atoms or something like that. And this configuration, you can see an image of this configuration here. And so the spins, in fact, what is characteristic is a local Wheeler spin on a small number of atoms. And in fact, they are induced by relativistic correction to quantum physics, what is called the spin-orbit effect. And that this spin-orbit effect leads to interaction that makes that the rotation is always, in this case, counterclockwise. And so when the system can be established in this configuration with always counterclockwise rotations, it cannot be detwisted, it cannot be unwound except by introducing a lot of energy. This is what is called the topological protection. The topological protection is a concept introduced by Mr. Skyrm in the physics of high energy, but it can be one of the realizations of this concept are this skyrmion in magnetism. And so it's like a Modius ring. You cannot twist a Modius ring to reproduce a usual ring. And in fact, and the property that then, once they are stabilized in this configuration, they can be moved like nanoparticles, like nanoballs on a BR. And so this new small particles, there are many quasi-particles in physics at the nanoscale, not only the electrons, the photons, the phonons, but also the pairs, the Cooper pairs, the exciton, etc. This is another type of quasi-particle which has the property to be able to, we can move easily with an electrical current, and also which is stable, with really stable, it can be, you stop the current, there is a steady, there is a non-volatile storage of the information. And so there is an interesting perspective, for example, to replace the hard disk. The hard disk is not ideal. Huh? There are a lot of hard disks, they consume a lot of energy in the data center. And actually, what consumes energy in the hard disk is mainly all the mechanical system here with the motor and so on. And so the concept with skyrmion is a restrict memory based on skyrmions where you hide the information not on the disk, but on a sort of track in which you write here, and the information is stored by some train of skyrmions and read another place. And so you have only a purely electronic system to store and read and manipulate the information. And there are also logic gates that have been proposed to treat the information stored by skyrmions by sending skyrmions in input of the logic gate to realize some operation, logic operation. And even in some other case, because I have introduced STT-RAM, less consuming energy STT-RAM will be also, because it is the moving skyrmion does not need a lot of energy, will be to have a STT-RAMs where the switching of the free layer will be not by changing its orientation, but by moving the schermions from outside to inside. Okay, so I suppose maybe I have it too long, I don't know. So I will stop here, and simply to say I thank you for your attention.